20 on January 1968, 15:39 GMT, Thule Air Base, Greenland. In the radar operations room, Staff Sergeant Calvin Snap watched a blip vanish from his screen. 7 miles southwest of the runway, a B-52G Stratofortress carrying 4 Mark 28 hydrogen bombs had lost cabin pressure, forcing the crew to bail out into the Arctic darkness. The aircraft, tail number 5802566, crashed into the frozen surface of North Star Bay at approximately 100 feet per second. Within minutes, perimeter radiation monitors registered levels 25 times background. The dosimeter chirps came faster. By 16:05, the 306th Bombardment Wing had activated emergency protocols designed for mechanical recovery, not radiological crisis. What operators expected, intact weapon containment, collided with what the meters showed: plutonium dispersal across 7 acres of ice. The contrast would define everything that followed. 21st of January 1968 began as routine. The B-52G, part of Operation Chrome Dome's continuous airborne alert, had departed Plattsburgh Air Force Base in New York 13 hours earlier. Chrome Dome missions kept nuclear-armed bombers aloft around the clock, ensuring rapid response capability during the Cold War's tensest years. This particular sortie followed the polar route: Greenland, then across the Arctic, back through Alaska. Standard procedure called for mid-air refueling every 8 hours. At 15:22 GMT, approximately 6 hours into the flight, the crew reported cabin heating malfunction. Arctic flying at 34,000 feet demanded functional environmental systems. Within minutes, temperatures inside the fuselage dropped below freezing. The pilot attempted emergency descent, but found controls increasingly unresponsive as hydraulic fluid thickened. At 15:38, with cabin temperature approaching -20 degrees Celsius, the pilot ordered the 6 crew members to bail out. They ejected over Bylot Sound, 12 miles from Thule. The unmanned B-52 continued southwest on autopilot for 90 seconds. At 15:39:41, it struck the ice of North Star Bay at a steep angle, approximately 7 miles from Thule's main runway. Impact velocity exceeded 100 feet per second. The aircraft carried 4 Mark 28 thermonuclear weapons, each with a yield of approximately 1.1 megatons. The bombs themselves did not detonate, their elaborate safety systems functioned as designed, but the conventional high explosives in the weapons' firing mechanisms did. The explosive force shattered the weapons' casings and dispersed their fissile cores across the ice. Each Mark 28 contained roughly 6 kilograms of weapons-grade plutonium-239 and an unknown quantity of enriched uranium-235. The crash also ruptured the aircraft's fuel tanks, releasing 225,000 pounds of JP-4 jet fuel. The fuel ignited on impact, creating a fireball visible from Thule's control tower. Black smoke rose into the polar twilight, temperatures hot enough to melt ice and vaporize metal. Within the burning wreckage, plutonium underwent rapid oxidation in the intense heat. When plutonium burns, it forms fine particles of plutonium dioxide, particles small enough to become airborne. Wind speed at the crash site averaged 12 knots from the northeast. The smoke plume, laden with radioactive particles, drifted southwest across the ice. At Thule's operations center, the first alert came not from crash detection but from perimeter radiation monitors. At 15:41, just 2 minutes after impact, automatic alarms triggered at monitoring station Echo 7, positioned 1.4 miles south-southwest of the crash site. The Geiger-Müller detectors registered 2.5 milliroentgens per hour, 5 times normal background. By 15:55, readings at Echo 7 had climbed to 12.8 milliroentgens per hour. Mobile survey teams dispatched to the crash perimeter reported surface contamination levels exceeding 25 milliroentgens per hour in multiple locations. The 306th Bombardment Wing commander, Colonel Donald MacPhail, faced immediate decisions. Chrome Dome procedures included detailed crash response protocols, but those protocols assumed mechanical failure, not radiological dispersal. The base maintained emergency response teams trained for conventional aircraft accidents, fire suppression, and medical evacuation. It did not maintain a specialized nuclear accident response capability. That expertise resided at other facilities, Lawrence Livermore National Laboratory in California, Sandia National Laboratories in New Mexico, Los Alamos in New Mexico, all thousands of miles away. Colonel MacPhail activated base emergency protocols at 16:05. Initial response focused on crew rescue. All 6 crew members had survived ejection, though the co-pilot suffered a broken arm and mild frostbite. Search teams located them within 3 hours. The navigator, Captain Curtis Criss, was found 9 miles from the crash site, having parachuted onto the ice. He later described watching the fireball from his descent, uncertain whether it represented conventional fuel or something worse. Concurrent with crew rescue, MacPhail ordered the crash site secured. Security police established a perimeter 1 mile from the impact zone. Access required authorization and dosimetry. At this stage, no one understood the full extent of contamination. The initial assumption, shared by base personnel and responding units, was that the weapons remained largely intact, their primary containment possibly breached, but their cores relatively confined to the immediate crash zone. That assumption began to erode as radiation surveys expanded. By 18:00 on 21st January, portable instruments detected elevated readings across an area exceeding 40 acres. The pattern suggested dispersion, not containment. Hotspots, locations with significantly elevated activity, appeared in apparently random locations up to 500 meters from the primary wreckage. Snow samples collected at 1930 showed beta activity of 50,000 disintegrations per minute per gram in some locations compared to background levels of approximately 10 disintegrations per minute per gram. The base's senior health physicist, Major Verlin Dreesen, recognized the signature. The high beta to gamma ratio indicated plutonium contamination, likely in oxide form. Plutonium-239, the fissile isotope in nuclear weapons, emits primarily alpha radiation, particles that cannot penetrate skin but cause severe damage if inhaled or ingested. The beta radiation came from plutonium's decay products and from other isotopes in the weapon cores. The relatively low gamma readings suggested that most of the radioactive material remained on the ice surface rather than forming a deep plume, but that was cold comfort. Surface contamination meant easy resuspension. Wind could lift particles. Personnel and vehicles could track contamination beyond the perimeter. By midnight on 21st January, the immediate fire had burned out, leaving a blackened scar approximately 150 meters across. Wreckage fragments, twisted aluminum, landing gear struts, engine components, lay scattered across the ice. Somewhere in that debris field lay the remnants of 4 hydrogen bombs. Recovery would require specialized equipment, trained personnel, and a clear understanding of what they were dealing with. At that moment, in the Arctic darkness, with temperatures dropping to -30 Celsius, none of those elements were fully available. The morning of 22nd January brought clarity of a particular kind. Daylight revealed the crash site's full extent. What had appeared in darkness as a contained impact zone proved, under examination, to be a dispersal field covering nearly 7 acres. The B-52's high-speed impact had not merely destroyed the aircraft, it had atomized portions of it. Wreckage fragments ranged from multi-ton sections of fuselage to particles too small to identify visually. Major Dreesen established a radiation monitoring grid across the site using portable survey instruments. The AN/PDR-27 radiation detection sets, standard equipment for nuclear accident response in 1968, provided dose rate measurements but struggled in the Arctic conditions. Batteries drained rapidly in the cold. Mechanical components seized. By mid-morning, 3 of 7 instruments had failed completely. Despite equipment difficulties, the survey revealed troubling patterns. Background radiation at Thule typically measured 0.1 to 0.015 milliroentgens per hour, standard cosmic and terrestrial background. At the crash site perimeter, readings averaged 2.8 milliroentgens per hour, nearly 200 times background. Within the primary debris field, readings exceeded 50 milliroentgens per hour in multiple locations. One hotspot, designated Alpha 1, measured 127 milliroentgens per hour at a distance of 1 meter from the source. These readings carried specific implications. The maximum permissible dose for radiation workers in 1968, established by the Atomic Energy Commission, was 5 roentgens per year, approximately 0.57 milliroentgens per hour for continuous exposure. Personnel working at the crash site would exceed annual limits within days, possibly hours, depending on their specific locations and durations of exposure. The radiation signature also revealed weapon core behavior. The Mark 28 thermonuclear weapon used a plutonium-based primary stage to initiate fusion. The high explosive lenses surrounding the plutonium pit were designed to implode it symmetrically, achieving criticality and triggering the fusion reaction. When the conventional explosives detonated on impact, they scattered the plutonium without achieving the precise geometry required for nuclear detonation. The result was mechanical dispersion, not nuclear explosion. But dispersion created its own problems. Plutonium oxide particles, once formed, exhibit remarkable persistence. They do not decay rapidly. Plutonium-239 has a half-life of 24,110 years. They do not dissolve readily in water. They resist chemical breakdown. Their primary danger comes from inhalation. If inhaled, plutonium oxide particles lodge in lung tissue, delivering continuous alpha radiation to surrounding cells. The biological effects unfold over years. Increased cancer risk, potential organ damage, genetic effects. For the workers who would spend months recovering debris from the Thule ice, this invisible threat represented the primary hazard. Major Dreesen's initial assessment, transmitted to Strategic Air Command Headquarters at 14 UMD on 22 January, outlined these concerns. The message noted that while external radiation levels posed manageable risks for limited duration work, the potential for particle inhalation and skin contact demanded immediate deployment of specialized protective equipment and monitoring capabilities beyond Thule's existing resources. The base's standard issue Arctic gear, parkas, insulated boots, mittens, provided thermal protection but no radiological barrier. Respiratory protection consisted of standard military gas masks, effective against chemical agents but not designed for fine particle filtration. Personnel lacked anti-contamination clothing, air-supplied breathing apparatus, or the continuous monitoring equipment necessary to track individual dose accumulation. That afternoon, Colonel MacPhail sent an urgent request to Strategic Air Command for a specialized nuclear accident response team. The message specified required capabilities: hot particle detection and removal, weapons assembly, disassembly expertise, plutonium handling protocols, contamination control systems, and medical monitoring for potential internal deposition. The request traveled through multiple command layers. Strategic Air Command forwarded it to Air Force Systems Command. Systems Command contacted Sandia National Laboratories and the Atomic Energy Commission's Division of Operational Safety. By evening, a response team was being assembled at Kirtland Air Force Base in New Mexico. The team included weapons designers from Sandia, health physicists from Los Alamos, and military nuclear accident response specialists. They would arrive at Thule within 48 hours, but 48 hours meant continued exposure for personnel already on site. Security police maintaining the perimeter worked 12-hour shifts. Fire crews remained on standby. Survey teams continued mapping the contamination field. Each hour of work added to accumulated dose, and without proper monitoring equipment, precise dose tracking proved impossible. By 18 on 22nd January, preliminary surveys had identified locations of 3 of the 4 weapon cores. Alpha 1, the highest activity hotspot, marked the primary debris field where most of one weapon had come to rest. Beta 2 and Gamma 3 indicated the locations of 2 additional weapons, their signatures somewhat lower but still clearly identifiable. The 4th weapon remained unaccounted for. Survey teams had not detected its characteristic radiation pattern anywhere within the mapped area. This discovery, or rather this absence, troubled the specialists reviewing data at Sandia and Los Alamos. 4 weapons had been aboard the aircraft. 3 showed clear signatures. The 4th's location remained unknown. Had it been ejected during the crash sequence, landing outside the surveyed area? Had impact driven it deep into the ice? Had the weapon's core been so completely dispersed that its signature blended into background? Each possibility carried different implications for recovery operations and long-term contamination. As darkness returned to Thule on the evening of 22nd January, the crash site took on an eerie quality. Generator-powered floodlights illuminated the central debris field, casting long shadows across the ice. Steam rose where warmer air from the generators met the -30-degree environment. Personnel moved carefully, watching dosimeters, avoiding obvious hotspots. The wreckage itself looked strangely peaceful under the artificial light. Torn metal and scattered components, all coated in a fine layer of frost. But the peace was deceptive. In the frozen ground beneath the visible debris, plutonium particles were settling, working their way down through microscopic cracks in the ice, beginning a slow migration that would continue for decades. The Arctic environment, so harsh to human operations, proved remarkably efficient at preserving radioactive contamination. The Specialized Response Team from the United States arrived at Thule on 24th January aboard a C-141 Star lifter. The team comprised 37 personnel, 14 weapons specialists from Sandia National Laboratories, 8 health physicists from Los Alamos, 12 military nuclear accident response personnel from the 1172nd Special Activities Squadron, and 3 Atomic Energy Commission observers. They brought 6 tons of specialized equipment including alpha particle detectors, continuous air monitors, anti-contamination suits, breathing apparatus, and portable decontamination systems. Dr. Dean McGovern, lead health physicist from Los Alamos, had participated in previous nuclear accident responses. He had been at Palomares, Spain in 1966, when another B-52 collision scattered 4 hydrogen bombs across farmland and ocean. He had worked at the Idaho National Engineering Laboratory following the SL-1 reactor accident in 1961. His experience provided framework for understanding what Thule represented, but the Arctic environment introduced variables absent from previous incidents. McGovern's first priority was establishing comprehensive contamination mapping. The preliminary surveys conducted by base personnel had identified major hotspots, but lacked the resolution and coverage necessary for recovery planning. His team deployed 53 monitoring stations across a 2-square-kilometre area, creating a grid with 100-metre spacing. Each station included an alpha detector, beta-gamma survey meter, and air sampling system. The monitoring network revealed contamination patterns more complex than initial surveys suggested. The primary debris field, designated Zone Alpha, contained the highest activity concentrations, up to 500,000 disintegrations per minute per 100 square centimeters in some locations. This represented weapons-grade plutonium in relatively concentrated form, likely portions of weapon pits that remained partially intact despite the impact. But surrounding Zone Alpha, distributed in an irregular pattern extending up to 800 meters in multiple directions, lay dozens of secondary contamination areas. These hotspots varied widely in size and intensity. Some covered only a few square meters with activity levels barely above background. Others extended across 50-meter zones, with readings sufficient to deliver annual radiation dose limits within hours. The distribution pattern told a story of dispersal mechanics. The initial impact had shattered weapon cases and scattered large fragments in the immediate vicinity. The subsequent fire had vaporized some plutonium, creating oxide particles that rode the smoke plume downwind. The explosion of conventional high explosives had projected other fragments outward at high velocity, embedding them in ice and snow hundreds of meters from the primary crash site. Wind, during and after the fire, had redistributed fine particles across the landscape. Recovery operations required careful sequencing. Dr. McGovern established a phased approach. First, remove large, easily identifiable fragments with high activity. Second, systematically survey and remove medium-sized contaminated debris. Third, scrape and remove the surface ice and snow across the entire contaminated zone. Fourth, conduct final verification surveys to identify any remaining hotspots. Phase 1 began on 25th January. Workers, now equipped with proper anti-contamination suits and breathing apparatus, approached Zone Alpha using a technique developed at earlier accident sites. They worked in pairs, with one person operating radiation detection equipment while another handled recovery tools. Communication proceeded via hand signals. The Arctic wind and bulky protective gear made verbal exchange nearly impossible. The first major fragment, designated Item Alpha 1A, consisted of a section of weapon casing approximately 40 centimeters in diameter, weighing an estimated 60 kilograms. Surface contamination exceeded instrument range, greater than 1,000 disintegrations per minute per 100 square centimeters. Workers used long-handled tools to manipulate the fragment into a lead-lined recovery container. The operation required 45 minutes. Afterward, both workers' anti-contamination suits showed detectable contamination despite careful protocols. This pattern repeated across Zone Alpha. Over 3 days, teams recovered 73 major fragments. Each recovery followed similar procedures: remote radiation survey, careful manipulation using tools to maintain distance, placement in shielded containers, personnel decontamination. The work proceeded slowly, limited by cold by the need for frequent personnel rotation to prevent excessive dose accumulation, and by the simple difficulty of working in bulky protective gear at -30-degree temperatures. Personnel dose management became a critical concern. Dr. McGovern established strict rotation protocols. No worker would accumulate more than 500 milliroentgens during the operation, with daily limits of 50 milliroentgens. Workers wore both film badges and thermoluminescent dosimeters with daily readouts to track accumulated exposure. By the end of the first week, 12 workers had approached their operational limits and were temporarily removed from contaminated area work. The Arctic environment created unexpected operational challenges. Anti-contamination suits, designed for use in temperate climates, became stiff and brittle in extreme cold. Zippers froze, gloves lost flexibility. Breathing apparatus face seals failed as moisture from exhaled breath froze around the edges. Equipment modifications occurred daily as teams adapted systems to Arctic conditions. Cold affected radiation detection equipment as well. Alpha particle detectors, which required thin entrance windows to allow particles to reach internal sensors, experienced window failures as the thin material contracted and cracked. Battery-powered instruments drained rapidly. Mechanical components seized. Some instruments required heated enclosures to function at all. The technical challenges meant that radiation measurements, despite best efforts, carried higher uncertainty than would be typical in more moderate environments. By 30th January, Phase 1 recovery had removed approximately 85% of the major fragments identified in initial surveys. The remaining 15% lay in locations that required additional preparation, areas where ice had refrozen over debris, or where subsurface contamination required excavation equipment. Phase 2. Operations focusing on medium-sized debris commenced on 1st February. Medium debris recovery demanded different techniques. These fragments, ranging from a few grams to several kilograms, lacked the intense radiation signatures of larger pieces. Locating them required systematic ground survey using portable alpha detectors. Teams moved across the contaminated zone in carefully planned search patterns, scanning every square meter of surface. The work revealed the crash's true scope. What appeared to casual observation as clean ice often showed, under careful survey, scattered particles of contamination. A single square meter might contain dozens of small fragments, each requiring individual recovery. The time required to completely clean even a small area extended beyond initial estimates. As February progressed, weather deteriorated. Thule's location, 76 degrees north latitude, meant winter darkness and severe storms. Wind speeds increased. Visibility dropped during frequent snow squalls. Work halted during the worst conditions, then resumed when weather permitted. The schedule, initially projected for 6 weeks of field operations, extended to 8 weeks, then 10. Throughout this period, the missing 4th Weapon Core remained unlocated. Survey teams expanded their search area to a 3-kilometer radius from the crash site. They surveyed the ice, drilled cores through suspicious areas, and deployed sensitive detection equipment across the region. The weapon's signature did not appear. Specialists began to consider the possibility that significant portions of the 4th weapon had been consumed in the fire or dispersed so thoroughly that individual particles fell below detection thresholds. This absence would haunt the operation's aftermath. Recovery efforts could claim success in retrieving 3 weapons worth of material, but without accounting for the 4th weapon's core, questions remained. Where had that plutonium gone? How much remained in the environment? What were the long-term implications for the region? By mid-February, Recovery operations had transitioned to Phase 3, removal of contaminated ice and snow. This phase represented the operation's largest challenge in terms of volume and logistics. The contaminated zone covered approximately 240,000 square meters. Even removing a shallow surface layer, the top 10 centimeters, meant handling 24,000 cubic meters of contaminated material. The operation required specialized equipment. The Air Force contracted with the Peter Kiewit Sons Company, a construction firm experienced in Arctic operations. Kiewit deployed excavators, front-end loaders, and transport trucks modified for Arctic service. The equipment arrived by airlift in stages during the second week of February. Work crews scraped the ice using bulldozers equipped with radiation-safe cabs, shielded enclosures that reduced operator exposure to acceptable levels. Scraped material was loaded into trucks and transported to a temporary storage area designated as the Contaminated Materials Holding Facility, established on solid ice 3 kilometers from the crash site. The volume of contaminated material exceeded initial estimates. Early planning assumed removing 10 centimeters of surface ice would suffice. Ground surveys revealed contamination penetrating deeper in many locations, particularly where crash-generated heat had melted ice, allowing radioactive material to sink. In some areas, crews needed to remove 30 centimeters or more to reduce readings to acceptable levels. Material handling procedures followed strict protocols. Each truckload received a radiation survey before leaving the crash site. Trucks showing contamination levels above 100 milliroentgens per hour at the surface required additional decontamination before transport. Drivers rotated frequently to limit individual exposure. Vehicle wheels were surveyed and decontaminated at checkpoints to prevent tracking contamination outside controlled areas. The Contaminated Materials Holding Facility grew rapidly. By 20th of February, it contained approximately 10,000 cubic meters of contaminated ice and snow, arranged in monitored piles surrounded by portable radiation barriers. The original plan called for this material to be containerized and shipped to a permanent disposal site in the continental United States. But shipping 10,000 cubic meters by air proved impractical. Storage capacity on available aircraft, combined with air route limitations and handling requirements, meant the material would require hundreds of flights. An alternative solution emerged: temporary storage at the holding facility through the winter, followed by sea transport during the brief Arctic summer when North Star Bay became navigable. This decision extended the project timeline by months, but provided a feasible path for material removal. The facility was expanded to accommodate projected volumes, eventually covering an area of 30,000 square meters, surrounded by security fencing and monitored continuously. As Phase 3 progressed, personnel accumulated dose records that would become part of the operation's controversial legacy. By 1st March, 201 workers had participated in the recovery operation. Their cumulative exposure totaled approximately 93,000 milliroentgens, an average of 441 milliroentgens per person. But this average masked significant variation. 23 workers had received doses exceeding 800 milliroentgens. 7 workers exceeded 1,000 milliroentgens. One worker, a heavy equipment operator who spent extended periods in the contaminated zone, received an estimated dose of 1,850 milliroentgens. These doses remained below the regulatory limit for emergency workers, 5,000 milliroentgens per event, but significantly exceeded normal occupational limits. The question of long-term health effects would linger for decades. Studies of radiation worker populations suggested that doses in this range carried measurable but small increases in cancer risk. Whether individual workers would experience health consequences remained statistically uncertain but biologically possible. The operation also generated concern about internal contamination. Plutonium particles that workers might have inhaled or ingested despite protective equipment. All workers provided urine and fecal samples for bioassay analysis, looking for plutonium excretion as evidence of internal deposition. Initial analyses conducted at Los Alamos National Laboratory detected plutonium in samples from 37 workers. The levels varied from barely detectable to approximately 0.3 picocuries per sample. These detections did not necessarily indicate dangerous exposure. The analytical techniques used in 1968 could detect plutonium at extremely low levels that might result from environmental contamination of samples rather than true internal deposition. Follow-up whole-body counting, using more sophisticated detection systems, found elevated plutonium only in 4 workers. Their estimated internal doses range from 10 to 80 milliroentgens, significant but not immediately dangerous. Dr. McGovern established a long-term medical surveillance program for all workers involved in the operation. The program included annual medical examinations, chest radiographs, and periodic bioassay sampling. The Air Force Office of the Surgeon General assumed responsibility for maintaining this registry and conducting follow-up studies. Over subsequent decades, this population would become one of several cohorts studied to understand long-term health effects of occupational plutonium exposure. By late March, surface ice removal had covered approximately 85% of the contaminated zone. The remaining areas required specialized handling, locations where bedrock lay close to the ice surface, or where structural concerns prevented heavy equipment access. These areas underwent manual decontamination using hand tools and careful survey techniques. The operation's environmental impact extended beyond radioactive contamination. Removal of ice and snow exposed underlying bedrock and sediment in some areas. Diesel fuel from generators and equipment leaked in small quantities. The construction of the contaminated materials holding facility required excavation and grading. The crash site itself, once restored, bore scars from recovery operations, an area stripped of natural ice cover, cut into geometric zones, marked by vehicle tracks and excavation patterns. Danish authorities, who held sovereignty over Greenland, had been involved in the operation from its outset. Denmark maintained an observer presence at Thule, and Danish scientists participated in environmental monitoring. Their concerns focused particularly on long-term contamination of the marine environment. North Star Bay connected to Baffin Bay and ultimately to the North Atlantic. Any radioactive material entering the water could potentially spread far beyond the immediate area. Water sampling conducted throughout February and March detected trace amounts of plutonium in North Star Bay. Concentrations measured approximately 0.01 picocuries per litre, 10,000 times lower than drinking water standards, but elevated above natural background. The source appeared to be runoff from melting contaminated snow and ice. Modelling suggested that plutonium concentrations would decrease as material dispersed through the bay and diluted into the larger marine system. Biological sampling provided another dimension of environmental assessment. Researchers collected fish, mollusks, and marine mammals from North Star Bay and surrounding waters. Analysis detected plutonium in some samples, particularly in bottom-feeding organisms that might ingest contaminated sediment. Concentrations remained low, typically below 0.1 picocuries per kilogram of tissue, but demonstrated that radioactive material had entered the food chain. The question of the missing 4th weapon core continued to plague the operation. Despite exhaustive surveys covering a 5-kilometre radius, the weapon's primary pit had not been located. Some specialists theorized that a significant fraction of the 4th weapon had been vaporized in the crash fire, dispersed as fine particles across a wide area at concentrations below detection limits. Others suggested portions might have sunk through ice cracks into the waters of North Star Bay, where they would be nearly impossible to locate. In April, a specialized underwater survey team arrived equipped with submersible radiation detectors. They surveyed the seafloor beneath the crash site, looking for high-activity sources that might represent large fragments. The water depth averaged 20 meters, with temperatures near freezing, and visibility measured in centimeters due to sediment suspension. Despite these challenges, the team conducted systematic surveys over a 2-week period. The underwater survey detected one significant source, designated Underwater Anomaly 1, showing activity levels consistent with weapon core material. Recovery operations retrieved a 15-kilogram fragment of material, later confirmed as enriched uranium from a weapon secondary stage. This fragment represented a partial account of the missing 4th weapon, but did not resolve all questions about its fate. As spring approached, attention shifted from immediate recovery to long-term restoration. The contaminated materials holding facility contained 12,700 cubic meters of contaminated ice, snow, and debris. This material awaited transport to permanent disposal, scheduled for August when North Star Bay would be navigable by ship. But restoration involved more than material removal. It required demonstrating that remaining contamination posed acceptable risk. Dr. McGovern's team conducted final verification surveys across the entire site, using more sensitive detection equipment than had been available during initial operations. The surveys identified 37 residual hotspots, locations where activity remained above background despite remediation efforts. These residual areas fell into three categories. First, locations where contamination had penetrated into bedrock cracks beyond practical removal depth. Second, areas where ice regrowth had occurred over contaminated surfaces, trapping radioactive material below new ice layers. Third, scattered locations where small particles remained despite repeated scraping and decontamination. The team addressed each category with appropriate techniques. Bedrock cracks received grouting with specialized materials to stabilize contamination and prevent migration. Ice-covered areas were marked for ongoing monitoring. Scattered particles were targeted with intensive hand survey and recovery operations that continued through May. By June, residual contamination across the site averaged 0.8 milliroentgens per hour, approximately 50 times higher than natural background, but below levels requiring active controls under existing military criteria for restored sites. The highest remaining reading, at a residual hotspot designated RHS-23, measured 15 milliroentgens per hour at 1 meter distance. Workers placed a concrete monument over this location, marking it for future monitoring. The cleanup's endpoint became a subject of technical debate. Some specialists argued for more aggressive remediation, continuing work until readings approached background. Others noted that attempting to reach background levels would require removing bedrock, clearly impractical, or would identify ever smaller particles in an asymptotic pursuit of perfection that consumed resources without meaningfully reducing risk. The Air Force, in consultation with the Atomic Energy Commission and Danish authorities, established restoration criteria. Average activity across the site not exceeding 1 milliroentgen per hour, with no individual accessible location exceeding 20 milliroentgens per hour without physical barriers. These criteria represented a balance between radiological safety and operational feasibility. In August, the USNS Boyce arrived at Thule to transport contaminated material. The ship, a military sea transportation service vessel, had been modified to carry radioactive cargo. Over 3 weeks, workers loaded 237 shipping containers with contaminated ice, debris, and soil. The containers, each weighing approximately 8 tons, were secured in the ship's hold with specialized bracing to prevent movement during transport. The Boyce departed Thule on 28th of August, bound for the Savannah River site in South Carolina. The voyage took 11 days through the North Atlantic and along the U.S. eastern seaboard. At Savannah River, the material underwent further processing and was ultimately buried in controlled disposal facilities designed for radioactive waste. Material removal marked the operation's functional conclusion, but monitoring continued. The Air Force established a long-term surveillance program for the Thule site, with annual surveys scheduled to track any changes in residual contamination levels. Danish authorities maintained independent monitoring through the Greenland Environmental Research Institute. These programs would continue for decades. The operation's cost became a matter of considerable interest. Published estimates placed total expenditure at approximately $9.4 million, significant for 1968 but modest compared to the strategic value of the weapons and the importance of maintaining Chrome Dome operations. The cost breakdown included $2.1 million for personnel and deployment, $3.8 million for equipment and logistics, $2.2 million for material transport and disposal, and $1.3 million for monitoring and restoration verification. But financial costs represented only one dimension of impact. The operation consumed 73,000 person-hours of work in contaminated areas. It exposed 201 workers to measurable radiation. It generated international controversy about nuclear weapons deployment and accident risks. And it raised questions about the Chrome Dome program's wisdom that would ultimately contribute to its termination. Personnel health monitoring revealed patterns that troubled medical experts. While no workers showed immediate radiation injury, 37 had detectable internal plutonium deposition. The long-term implications remained uncertain. Plutonium in lung tissue delivers continuous radiation exposure for years or decades. Cancer risks increase gradually. Detecting whether any individual worker's future cancer resulted from radiation exposure versus background causes would be statistically impossible in most cases. The Air Force nevertheless committed to lifetime medical surveillance for operation participants. The program included annual examinations, chest radiographs every 3 years, and whole-body counting every 5 years. Workers reporting health concerns received priority evaluation. This commitment, while well-intentioned, proved difficult to maintain as participants moved, retired, or simply lost contact with military medical systems. By 1975, medical surveillance had been maintained for 189 of the 211 original participants. Of the remaining 22, 8 had died from causes unrelated to radiation, 7 had been lost to follow-up, and 7 had declined further participation. No participant had yet developed cancers clearly attributable to radiation exposure, though several had diagnoses, lung cancer, leukemia, that could potentially be related. Decades later, epidemiological studies of the Thule worker population would find modestly elevated cancer rates compared to general population baselines, but the small sample size and multiple confounding factors made definitive conclusions impossible. The studies could neither definitively prove nor conclusively rule out health effects from the operation. The legacy extended far beyond immediate restoration. Plutonium in the Arctic environment behaves according to principles of geochemistry and biology that operate over timescales measured in centuries. The half-life of plutonium-239, 24,110 years, means that material deposited in 1968 will remain hazardous essentially forever on human timescales. Environmental monitoring conducted in the years following cleanup revealed patterns of contamination persistence and migration. Seawater samples from North Star Bay showed declining but detectable plutonium levels through the 1970s. Concentrations decreased from peak levels of 0.01 picocuries per litre in 1968 to approximately 0.001 picocuries per litre by 1975, reflecting both dilution and sedimentation of particulate material. Marine sediments told a different story. Core samples collected from the bay bottom showed plutonium concentrations of 5 to 15 picocuries per gram in surface sediments, declining to near background levels at depths below 20 centimeters. This vertical profile indicated that plutonium had bound to sediment particles and settled to the sea floor, where it would remain largely immobile unless disturbed by bottom currents or biological activity. Biological concentration provided another pathway for contamination persistence. Certain marine organisms, particularly bottom-feeding mollusks and crustaceans, accumulated plutonium at levels exceeding their environmental concentrations. Bioconcentration factors of 10 to 100 were documented in some species. This meant that animals feeding on contaminated sediment might contain plutonium at levels 10 to 100 times higher than the surrounding water or sediment. Fish consumed by local populations showed lower but still detectable plutonium levels. Samples of Arctic char, a staple species for Greenlandic residents, contained 0.01 to 0.05 picocuries of plutonium per kilogram of tissue. These levels remained far below health concern thresholds. Consumption of such fish would deliver radiation doses thousands of times lower than natural background, but demonstrated that contamination had entered the food chain. The Inuit communities living in the Thule region faced particular concerns. Traditional subsistence activities depended on marine resources. Seals, walrus and fish from North Star Bay and surrounding waters formed important dietary components. The question of whether these resources remained safe generated anxiety and distrust. Danish and Greenlandic health authorities conducted risk assessments based on environmental monitoring data and dietary consumption patterns. The analyses concluded that radiation doses from consuming local seafood remained negligible, less than 1% of natural background radiation exposure, but numerical reassurances often failed to overcome concerns rooted in violations of trust and cultural impact. The crash and subsequent recovery operations had occurred on land traditionally used by Greenlandic Inuit. The establishment of Thule Air Base in 1951 had already displaced a community from their ancestral territory. The 1968 crash represented another intrusion, another contamination, another instance of external forces disrupting traditional life. These grievances extended far beyond radiological risk into questions of sovereignty, compensation, and respect. In subsequent decades, Greenlandic political movements would cite Thule as evidence supporting independence from Danish governance and opposition to foreign military presence. The contamination became symbolic of broader patterns of colonial exploitation and environmental injustice. These connections between radiological incident and political consequence illustrate how technical events carry social implications that extend far beyond their immediate physical impacts. Environmental research continued at Thule for decades. Studies in 1978, 1984, 1991, 1997, and 2003 all included sampling and analysis at the crash site and surrounding areas. The pattern remained consistent. Residual contamination persisted at low but detectable levels, concentrating in sediments and in certain biological organisms, declining very gradually through dilution and decay. The 2003 study, the most comprehensive, employed modern analytical techniques unavailable in 1968. High-resolution gamma spectroscopy and alpha spectrometry detected plutonium at concentrations below 1968 detection limits. The study found that while contamination had declined significantly, it had not disappeared. Plutonium isotopes remained detectable in sediments, in ice, and in some biological samples. The total inventory of residual plutonium, the amount remaining in the environment after cleanup, was estimated at 1 to 3 kilograms, a small fraction of the original weapon core mass but still substantial. This residual inventory posed minimal direct risk. The doses delivered to any individual from environmental exposure at Thule measured in the microrems range, millions of times smaller than doses received by recovery workers and thousands of times smaller than natural background. But the symbolism remained potent. Nuclear material from US weapons contaminating Greenlandic territory created lasting tensions. The question of the missing fourth weapon core never received complete resolution. Despite exhaustive surveys and multiple search operations, significant portions of that weapon were never recovered. The most likely explanation: dispersal as fine particles across a wide area, some of which entered the marine environment, suggested that this material had become unrecoverable. It remained in the Arctic environment, distributed too thinly to locate but collectively representing perhaps a kilogram or more of plutonium. This unrecovered material guaranteed that Thule would remain a contaminated site essentially permanently. The plutonium would decay on its own timescale, independent of human activities or preferences. Cleanup had removed the vast majority of material and had reduced risks to acceptable levels, but it had not and could not restore the site to its pre-accident condition.